Hello everyone, welcome to my channel. In this video, we'll be seeing how to do assembly programming for ARM-based microcontrollers. Basically, in this video, majorly we'll be focusing on drafting assembly program for STM32 F401 RET, and the agenda of this video will be knowing the syntax to write the assembly code and delving into the instruction set, knowing about CPSR, which is most important for ARM-based microcontrollers, and what is the significance of branching instructions, significance of labels, and method to convert a C code to assembly code. Here we'll also be seeing what are the alternative ways to write assembly code from algorithm, and the final agenda will be performing selection sort using assembly programming. And coming to the first one, syntax to write assembly code. Syntax will be, you will be setting your title, TTL, some random title, and area. You can keep any area, any name here. Like you can keep area P1 also, area P1. Code read only. These are mandatory. And export whatever the main function you are writing. The title of the main function you have to keep here. I have kept it as sort small large main. So whatever the name you have written here, you have to write here and start writing your code implementation, assembly code. Once it is done, you have to write here be here. Here be here is nothing but similar to while one bodiless, and end is nothing but you are telling the compiler that this is the end of my assembly code. And once after the syntax, we will see the basic storing instructions. So ARM based microcontrollers basically use load store architecture. That is, you can either load from the memory cell or store into the memory cell. So what does this mean is, whatever the data present in the address of Rx, for example, if I have something like 0x20000000, this is the address. Here I have number called 21. If I want to take this into my register 1, what I'll do is ldr r1 comma r2. Before this, what I'll do, move r2 comma, or simply move, instead of move, let us use ldr only. So here you can write ldr r2 comma is equals to 0x20000000. So what happens now is, R2 is having the address of the value 21. Now if I want to load the value at the address of R2, I'll write value at the address of R2 is loaded into R1. This is what the syntax for load. So in load we have two variants, load B and load H. Load B is nothing but you will load 8 bits once at a time. Load H will load 16 bits. This is abbreviated as LDR byte, LDR higher byte. So why it is used is, for example, you are using your assembly program for UART application. UART application will take 8 bits at a time. In that case, you can load 8 bits one time. And store is reverse of load. So what happens is, if you write something, let us say if I want to store value in the R3, str R3 comma R2. What now? Now what will happen is, whatever the value present in R3, that will be overwritten in the address of R2. So in R2 we have 0x20000000. If I write store R3 comma address of R2, what happens is this value gets written into that address. In store also we have store byte and store high. Here 8 bits will be 8 bits will be stored, 16 bits will be stored in this case. And next, coming to arithmetic operations, these are most important. So every arithmetic operation has two variants. One is any arithmetic operation or any operation. One is simple operation, and one it is preceded with s. This s suffix means you are setting the flags. That means whatever the addition or multiplication or subtraction you are doing, the effects will be shown on the flags. What are flags and how they will be affected, we'll be seeing in the further slides. If you are interested in knowing about each of this, you can pause here and view each of the uh, instruction and its description. Moving forward, we have CPSR. CPSR is nothing but current program status register. This current program status register holds several flags. Out of them, the major one is C, Z, N, and V. we'll mostly be using C and Z only, and sometimes N. V we rarely use. So C is the carry flag. How it is affected is nothing but, for example, if you are performing an addition operation and your carry is generated. So whenever carry is generated, this C bit will become 1. So zero flag. How the zero flag will be affected? For example, if I am doing exclusive or operation with R1 comma R1, now what happens is all the contents of R1 will become 0. Now the 0 flag will be enabled. How the negative flag will be enabled? Whenever you are subtracting two numbers and the resultant is negative, then the n flag will be enabled. The overflow flag will be enabled during the addition of two numbers, where in which the higher byte overflows from the available memory space of the registers. Now coming to how these flags are affected, always please remember the whatever the instruction in which you are using the flags, that will be reflected in the preceding instruction. For example, here if I write something like here if here I have, let's say, instruction 1, instruction 2. In instruction 2, if I want to use the effect of carry flag, like if I want to write something, let us say if carry is equals to 0, this carry is equals to 0 preceding instruction must be the instruction such that it will affect the carry flag. That means this must be either something like add uh, something b1, sorry, r1 comma r2, or some other instruction which might affect the carry flag. The reflected carry flag effect will be shown in the succeeded instruction only. So these are the different flags. So moving forward, we have branch instructions. So what is the significance of branch instruction is, in C programming we have so many, like we have if, we have if else, we have else if ladder, and we also have conditional operator. So in assembly programming we don't have all this. Instead we have only branching instructions. For branching instructions, what we do is we have two methods. One is based on CMP. CMP is a function compare Rn comma operand 2. So if you are taking two numbers and comparing them, based on the resultant of the comparison, we have several branching instructions. So we have BCS, which means if the first operand is greater than the second operand, this branching will takes place. For example, if I write BCS loop, so if the first here before writing this, I have to compulsorily write CMP R1 comma R2 or any register, so that whatever the flags affected, that will be uh, used in the BCS function, BCS instruction. So BCS loop means if R1 is greater than R2, the program control will be transferred directly to the label where the loop is written. Similarly, we have BCC, BEQ, BNE, BLS, and BHI. So if you are interested in looking at it, please pause here and take a screenshot or look at it. Moving forward, we have another type of branch instructions, wherein we are not using directly the compare function, but the flags are getting affected. For example, as I mentioned in the previous slide, adding a suffix s to the arithmetic operations will affect each and every flag in the CPSR. Now let us take an example. If you take r1 is equals to 10, and if you have loop here, and you are making subs r1 comma, let's say here you take r2 is equals to 1 also, r1 comma r1 comma r2. So this will result in r1 is equals to r1 minus r2. Now what happens here, I'll write bne loop. So what will happen here? For first time, SBS sub s 10 will be equal to 10 will become 9, 9 will become 8, 8 will become 7, until this becomes 0. BNE nothing but branch if not equal. That is, if 0 is equal, if z is equal to 0, it will not branch. Sorry, it will branch. If branch like if the preceding instruction is resulting a value which is 0, z becomes 1, then the branching will not happen. So what happens is, for example, if I have a let's say if I have some lines of code above these instructions and some lines of code above these instructions, until r1 becomes 0, the instruction program control will not transfer from this loop to other instructions. So this is the advantage of using branch instructions along with labels. So these are some of the methods. Moving forward, we'll see the significance of labels. So in order to understand the significance of labels, you have to understand the significance of go to statement. In C programming, if you are familiar with go to statement, we were using go to statement like in the starting years of engineering, like for developing a calculator or any do while loop. Before these loops were introduced, only go to statement was used. Go to functions like this. For example, let's say here I have jump. Let us keep a case label as jump, and I will write I is assigned with 0. Sorry, instead of I is assigned with 0, let us take I is assigned with I plus I minus 1. And if I is equals to I is not equal to 0, so for that we have to use not equal symbol. Okay, just a minute. I is not equal to 0. Let us say go to jump. Now what will happen is, until I becomes 0, the program continuously moves from these go to jump to go to. This continues until I becomes 0. In the same way, in assembly program also, labels we will be using. We call this as label, but in assembly we won't keep this. We just keep jump, and instead of go to, we have some other instructions, like mentioned in the previous slides: BCS, BCC, BEQ, BNE, BLS, and BHI. These are used instead of go to. And coming to converting C code to assembly code, in order to convert a C code into assembly code, we have to follow some steps. So we have to write the code in C and replace all the loops that are present in the code with go to statements. That is, for example, your code has something like for I is equals to 0, I plus I is less than 10, I plus plus. Then you have to look for an equivalent go to statement that can suffice this for loop, so that the code functionality won't change. And once you are done with replacing all loops with go to statements, you have to analyze the if condition. Why I am saying if condition is, even if condition is also like a uh, label based statement only. For example, if you have something like if k is equals to 0 and you have some set of code to execute, this will be executed only if k is equals to 0. But what if k is not equal to 0? This code should not be executed. So, practically speaking, if you think in the assembly programming perspective, here you must have something like a case label that will decide whether you have to jump from this statement to this statement. Let me simplify this for you. For example, if you have something like if k is equals to 0, this is the set of instructions you have to execute. So, if you want to convert this into assembly, what you must have is, let us say something like if it is BEQ, branch if equal jump, sorry, BNE. Here you will have all the set of code that you similar to the code you will be executing here, and here you will have the statement jump, and here you will have the remaining code. What are the remaining code here you are putting, you'll keep them here, because branch if not equal means if the preceding instruction, whatever you are keeping here, it is not resulting in a 0 result, then what happens is this will directly jump to here. Similar to this, if k is not equal to 0, this will not be executed, it will come here. So you have to think in the manner that if statements are also to be converted into branch statements with case labels. So once you are done with analyzing if statements and case statements, you have to replace the if statements with compare statements. Like if you had if k is equals to 0, right? You can have cmp k comma 0, and then you can have something like BQ or BNE. As mentioned in the previous slides, you have several statements, right, using compare. Like you can have this statement BEQ: if k is equals to 0, it will branch, or else it won't. So based on that, you can choose any of the branching statement. Once you have replaced all the if statements with compare statements, you have to replace the go to statements also with a branching statement with a proper branching instruction. In order to do that, what you have to do is, for example, if I'm writing go to let's say some temp, before writing go to in C, mandatorily we'll have some if statement controlling this go to statement. So you have to look at that if statement. For example, if you have something like if k is equals to 0, go to temp, then what does this mean? If k is equals to 0, branching should happen. So if k is equals to 0, branching should happen means, if you look in this compare thing, you have something like cmp k yeah, cmp k comma 0. So this will result, if k is equals to 0, 0 flag will turn on, and then you can write beq temp. So what will happen if k is equals to 0? Branching will take place. In this manner, you have to analyze every go to statement and replace them with branch instruction along with the label. Once you have done with replacing them, you have to replace all the storage instructions. Like for example, you have temp is assigned with a of I is assigned with I plus 1, with arithmetic instructions and load and store architectures. Like if you have something like I is assigned with I plus 1, you have to replace it with add I comma 1, something like this. Or instead of 1, you can keep r1, wherein you can assign r1 with, let's say, 1. This is just an example. You cannot use I directly. You need to have proper registers in order to do assembly programming. Once you have done everything properly, your assembly code will be ready. So let's move forward and see the alternative procedure. So alternative procedure is, you can always use the existing algorithmic flow, algorithm design, in order to draft an assembly program. This is the best procedure that one can adapt to write an assembly program, because if you observe here, this is the algorithm flow for selection sort algorithm. Let us say I have n is equals to 10. I'll assign I with 0 initially. I'll assume that small is I, that is the first element, and then I'll start from the second element and start comparing if any of the element is less than the first element. If it is so, I'll take the position of the element, and then until all the elements in the array gets exhausted, I'll be continuing this. Once all the elements in the array gets exhausted, I will swap the first fixed position element with the smallest element, and then proceed to the next element, which is I plus plus, and check if all the numbers are exhausted. If they are exhausted, stop there. If they are not exhausted, continue doing the process. This is the algorithm for selection sort. So we will come back to this later once we see the C code and assembly code. So the problem to be solved here is, we have to write ARM assembly to read 10 element integer array from SRAM address 0x200000 and sort the list in ascending order, and also we need to store the largest and smallest samples at 0x20000100 and 0x20000200 respectively. So basically what he is asking is, we have to sort the array and then take the smallest and largest number and store it in two different places. So moving forward, as mentioned in the first place, we have to write the C code. All of you are familiar with selection sort algorithm. I have just taken a compile time array, which is which is of length 10, and then I have written selection sort. For selection sort, it will be I will be ranging from 0 to n minus 1, and j will be ranging from I plus 1 to n. So once you are done with writing selection sort, next part will be replacing all the if statements with go to statements. If you want to know how I have replaced it, if you can see here, I have, for I is equals to 0, I is less than 9, I plus plus. Simply remove this I is equals to 0, keep it outside the loop, and I plus plus you remove it. Just before the loop is ending, you have to keep I plus plus. And coming to I less than 9, this will be your base case, base condition. So for that, what you have to do, once I plus plus is ending, you will write if I is less than 9, go to jump 1, let's say. Here you will remove everything, you will take off the for loop, you will remove this. Here you will keep jump 1. Similarly, you perform for this inner for loop also. So once you are done with it, you'll get something like this: jump 1, jump 2, and based on if statement, you'll get a jump statement. As mentioned earlier, the initialization will be kept out of the uh, loop, and whatever the updation, that will be just before the go to statement. Here also, updation is just before, initialization is outside of for loop. And ignore this. This I have just written to debug my code whether it is working fine or not. And now you are done with replacing all of these with the go to statements. Now let us move into the actual assembly program. You might think the code is a little bit lengthier, but let's delve into understanding this chunk by chunk. So let's come back to the algorithm that what we have seen here. How many dimensions you have? 1, 2, and 3 diamonds. So blindly you fix for every diamond there will be a case label. So we have 3 diamonds, we'll have 3 labels. But here we taken into consideration of just sorting the array. We even if we have to take care of storing the largest number. So for that we might get one more diamond. So total we will have 4 diamonds. So let us see if we have same number of case statement. 1, 2, 3, 4. Yes, we have same 4 diamonds corresponding to 4 labels. So first step we are done. And ignore this here be here. This is just like bodiless while loop running at the end of every embedded program. So let us start. So as he has asked to start the array from 0x2 0000000, we will take the address into R0 and take the number of elements into R1. If you observe here, I have used several registers just to make sure that I am not uh, tampering any data. Like for example, if I was using any register in a loop, I should not tamper that register in another loop so that complete loops will get disturbed. So I have used new register for each and every loop so that the data is kept intact. So if you observe here, this is just a copying operation because I am copying the value of R0 into R9. Once I have copied the value of R0 into R9, I am assuming that every integer is of 2 bytes. So I have to transfer 16 bits at a time. So I'll continuously use LDRH and STRH instructions only. For when I am dealing with data, please remember only when I am dealing with data. So next will be moving R2 is equals to 0. So I'm assuming that this is the largest number. It is important to know which will be the default value of a register holding the largest number and which will be the default value of a register holding the smallest number. The default value of register holding the largest number will be 0, and hold that the one that of holding the smallest number will be the largest value of the register. So for largest value, smallest value of register will be the default. For smallest value, largest value of register will be the default. So once you have assigned two registers for holding smallest and largest, which are R2 and R3, you can keep them aside, R2, R3. And now we will start our main loop. M loop stands for main loop. So here what we have done, we have moved R4 comma R1. What R1 is holding 10. So once we have moved R1, what we are doing is we are initializing a for loop, that is for I is equals to 0, I is less than 10, I plus plus. I am talking about this for loop. So what we are doing inside this for loop. So once you have initialized R4 comma R1, you are subtracting 1. This is just like a updation statement. So you are subtracting BEQ. What does this mean? So if you are subtracting this is nothing but R4 is assigned with R4 minus 1. So if R4 is equals to 0, no need to execute these all. Jump to E loop. That means, for example, if you have written a for loop, I is equals to 0, I is less than 10, I plus plus, and you have some set of instructions. If this primary condition is failing, then no need to execute these all. You can execute the instructions that are kept after the for loop. So for that, I have written a statement known as E loop, which will deal with storing the largest and smallest values at the specified registers given in the question. Once after that, what I am doing is, uh, this is the base statement. So if this is not failing, beq won't be executed, and we'll be moving into the next step. In the next step, we are taking the first element of the array, which is at the location of r9, into r5. Once we have taken the first element of the array, what we are doing is, we have to assume that is the smallest element. So I am assuming smallest element is in R6. And next, this is for starting of my another loop. Inside the for loop, we have another loop which is j, right? For j is assigned with I plus 1. So for that, I am taking another loop. This is for inner loop. Inner loop. So if you observe, for inner loop, I'm adding 2. Why I'm adding 2? I have assumed that the size of the integer is 2 bytes. So I'm adding 2 so that the address will be moved further by 2 bytes. So for example, if my initial I value is at 0, I have to move to I is equals to 1. This is the similar one. Like, instead of I is equals to 1, here we are updating it by 2, assuming that size of integer is 2 bytes. So once you have updated it, you will take the value, you will compare with R5. Why you are comparing with R5? You have pre-assumed that R5 is holding the smallest value. So we have assumed that smallest number is residing in the R5. So because we have loaded that from the R9, which is the first element of the our set of elements. So once we have taken that R5, we are comparing it with R7. R7 is the one which is taken in the inner loop. So if you, for your clarity, let us compare only our C code and the code that we are doing, assembly code. So first we have taken this I value, that is, we have taken this 9 value into a register, and after that we have taken this small value into R5. And once we have taken the small value into R5, we have started this J loop. So where we have started this J loop, we have started the J loop here. What is J here? R6 is J. R6 is equals to J. And then what I am doing, evaluate the address of R6, I am copying into R7. R7 is my buffer. I am comparing my buffer with R5. If R5 is less than R7, R5 is my target main, what to be sent. R5 is my small variable small. So R5 is like variable small. So if R5 is less than R7, it is obvious, no need to swap and do something. So you can move from this instruction directly to here. What if R5 is not the smallest one? Now you will move the smallest number into the R5, and what you will do is, you will take back the R6 value into R8. What is R8? Your whatever the value of you are referring to, this is an updation statement, because here you are using only R8, right? So whenever you are using R8, whenever you are using R8, you have to update it, right? That is the reason what we are doing is, I am updating R6 here. If you can see, R6 is updated as +2, and then I am taking back into my R8. So what I am doing is, here, previously here we are just updating J and even looking at J. Now what I am doing, I am giving J to some variable K. I am updating K and taking back the value of J and comparing the value of J. So if you understood, I am not directly taking the value of K or J, because as I mentioned earlier, to avoid tampering of data, I have used different registers for every purpose. So once you have done that, you need to subtract the R4 by 1, because in R4 what you have is the value of n. So as I mentioned earlier, the inner loop also must run n times. So you will subtract 1 from R4, b n e. If R4 is not 0, you will repeat the loop again until the smallest value is residing at R5. Once the smallest value is residing at R5, you will load the value into R10. what value you are loading into R10, whatever the first data you have taken. If you can see, in this is the main loop. Inside the main loop, you are taking the value from an address known as R9. So this data you are taking, copying into R10. So this is basically a normal swap operation. You are loading the value of R9 into R10, keeping R10 into R8, and again loading back to R5. So once you are done with swapping, you will just increment the main loop, that is I plus plus, which you are doing here, R9 comma R9 comma plus 2. And after that you have to also decrement the value of the n, which is kept as 10, because in selection sort the range of first loop will be from I is equals to 0 to I is less than n minus 1, and the second loop will be j is equals to I plus 1 until j minus n minus I, until j is less than n minus I. So for having this n minus I am decrementing manually the value of n, so that whatever the n minus I am doing, that will be reflected in the inner loop as well. BNE M loop, that is if R1 is exhausted, you can move further to storing the uh, biggest value and the smallest value. If R1 is not exhausted, you can go back and repeat the process. So this is the basic explanation of the selection sort algorithm. Thank you for watching. If you find this video interesting and informative, please do share this with your friends, and please do subscribe to my channel Tech Talks. Thank you.